Hi, this is Steve Taranovich, contributing editor to EDN, and I'm joined by Jamshed Khan, Avago factory applications engineer. Hey Jamshed, the solar power inverter card from SMA's Sunny Boy series has an Avago HCPL 316J and HCPL J312 isolated gate drivers on board. And I'd like to take some time to discuss the importance of isolation in solar power inverters, including topics and issues such as optical isolation advantages in transformerless solar power inverter products, and what challenges Avago's isolation solutions overcome to enhance the overall product performance. First question I would have is basically, what are some of the primary factors a designer would consider in selecting the optimum gate driver in a power inverter application?
Some of the primary factors a power designer would consider in selecting an optimum gate driver are higher output peak current capability. They should be energy efficient and power efficient. They should have small form factor or smaller printed circuit board footprint area. They should be cost effective and lower bill of material costs. They should have higher insulation capability, such as higher working voltages. They should have higher isolation or higher common mode noise rejection capability. They should have high quality, high reliability, and low degradation. And in addition, higher integration with useful protection features such as DSAT fault detection, under voltage lockout, and soft shutdown to prevent DI/DT spikes in the system.
Okay, great. Now, why would someone choose the Avago HCPL 316J and the HCPL J312 isolated gate drivers?
Some of the performance features of the HCPL-316J gate driver optocoupler are: it has very high output peak current capability of 2.5 amps. It has optically isolated fault feedback to the microcontroller. It has built-in desaturation fault detection for the IGBT or MOSFET protection. It has under voltage lockout protection. It has very high insulation voltage capability, such as a working voltage of 1230 volts peak, transient over voltage of 8000 volts peak, and insulation withstand V sub ISO of 5000 volts RMS per minute. Also, it has very high common mode noise rejection capability of 15 kV per microsecond at a common mode voltage of 1500 volts. The HCPL-J312 is also a 2.5 amp output peak current driver, but without the additional DSAT and fault sensing feature of the HCPL-316J. The UL isolation withstand voltage is 3750 volts RMS per minute and a working voltage of 891 volts peak.
Nice specs and features. Are there any newer isolated gate driver devices with more features that the designers of a solar inverter might want to consider?
Yes, we have many more newer gate drivers that the designers of the solar inverters may wish to consider for their future designs. More advanced gate drivers to replace the HCPL-316J would be the ACPL-332J and ACPL-333J. These gate drivers also have desaturation fault detection feature, but in addition, they also provide Miller clamp feature and a LED input control. The Miller clamp allows designers to eliminate the negative gate drive. The ACPL-H342 would be a good replacement for the HCPL-J312. The ACPL-H342 is also a 2.5 amp peak output current driver and has rail-to-rail output voltage swings with active Miller clamp capability. It has ultra-high common mode noise rejection of 40 kV per microsecond. The maximum power supply detector current is only 2.5 milliamp, which allows for a bootstrap power supply steam capability.
And what are some of the primary reasons that the designer should consider optocouplers in their gate drive applications, especially if the solar inverter is transformerless, which is allowed in Germany and some other countries in Europe, but not the US? Well, it is the US actually. Recently, it's been allowed in the US.
Transformerless inverters have been slow to enter the US market because of safety concerns and regulatory requirements. However, since 2005, National Electronics Code in the USA allows transformerless inverters to be used in the USA through specifying new safety requirements. The UL standard 1741 for photovoltaic and battery-powered inverters now includes requirements on transformerless inverters for the first time. Therefore, a few primary and overriding reasons for selecting optocouplers in such transformerless inverter applications are insulation or high voltage safety standard certified protection capabilities. Optocouplers provide reinforced insulation and in the event of a fault provide fail-safe protection. Isolation or common mode noise rejection capabilities. Avago Technologies' proprietary internal shielding technology within the optocoupler package allows an ultra-high common mode noise rejection. Other factors such as quality, reliability, small form factor, speed, power, and cost are also important considerations.
Great. Yeah, I know some of your Avago designers probably worked with some of the SMA designers in the implementation of the isolation in the inverter. What obstacles or challenges might designers have had to overcome in these kind of design?
IGBT or MOSFET protection is one of the primary design objectives in inverter applications. The HCPL-316J has an integrated desaturation fault detection feature that actively monitors the collector emitter of the IGBT or a MOSFET. And if for some fault reason, such as a short or a underdrive, the IGBT goes out of saturated state, the desat feature triggers an immediate soft shutdown, followed by a hard shutdown. In parallel, an optically isolated fault signal is immediately sent back to the microcontroller. The intrinsic power dissipated by the HCPL-316J or the HCPL-J312 is very low, with maximum DC quiescent current of only 5 milliamps. This ultra-low power requirement for the gate driver immensely decreases the complexity in the design and implementation of a simple bootstrapped power supply design.
Right. And since the physical spacing is mandated by safety standards, how does optocoupler size compare with alternative isolation solutions?
Alternative isolation technologies at the present time include magnetic and capacitive isolators. The much higher distance through insulation, DTI, and internal high voltage dielectric insulation layers within the optocoupler, along with the larger external creepages and clearances of the optocoupler packages, allow optocouplers to achieve the following. Number one, higher reinforced insulation levels with higher working voltages, higher ESD capabilities, higher transient over voltages, higher insulation withstand voltages, and wide optocoupler packaging offerings with diverse creepage, clearance, and DTI numbers for each package type offered allows optocouplers to meet different equipment safety standard requirements.
Right. Reliability is very important in these industrial designs since downtime in many applications means a great loss of revenue. How do optocouplers rank in mean time to failure, MTTF?
Avago's optocoupler reliability data sheets and alternative isolators use different activation energies in Arrhenius equations to calculate the mean time to failure and acceleration factors. This means that the MTTF provided by Avago Technologies and other competitor suppliers do not represent the equivalent failure rates. Hence, it will not be apples to apple comparison or ranking. Avago performs rigorous reliability stress testing under the worst case conditions of power and temperature to provide the MTTF and FITS information in the reliability data sheet. The MTTF and acceleration factors allow extrapolation of failure rates from the accelerated test conditions to actual use conditions. The MTTF information then allows one to calculate a failure rate per some time period. For example, expected percentage failures per year.
Okay. And energy savings and efficiency are very important also to power inverter manufacturers and their customers. Do optocouplers contribute to increased efficiency in these types of design architectures?
Emerging green standards require highly reliable and energy-efficient devices in small form factor and cost-effective or low-cost solutions. Avago gate driver optocouplers meet this criteria criteria by providing extremely high output peak current while consuming very low quiescent DC current and power. Avago gate drivers are also very fast and have very low propagation delays and propagation delay differences between any two devices. The form factors in SO8 packages, standard DIP packages, and SO16 packages is also very small. Thus, combining high output peak currents, fast speed response, small form factors, and cost-effective solutions allow Avago to meet the emerging green standards power delivery requirements.
Now, how would a designer handle safety functions needed in an IGBT or a MOSFET gate driver like desaturation, fault detection, undervoltage lockout, reporting fault status to the microcontroller?
Avago provides a wide array of gate driver optocouplers that have various levels of sophistication, integration, and features built into them. There is a family of sophisticated and highly integrated gate driver family that Avago provides that has the following features: desaturation fault detection, undervoltage lockout, optically isolated fault signaling back to the microcontroller, mirror clamp capability, and soft shutdown. The latest gate driver family with such advanced features and more is the ACPL-33J and ACPL-332J family.
Now, what if I need more output current on my gate driver than a typical optocoupler driver has?
In order to achieve higher output peak current than is available from the gate driver optocoupler, one can simply integrate an external NPN-PNP buffer amplifier at the output of the gate driver optocoupler.
Great, Jamshed. This is some wonderful information. I know our audience will gain very well from this. So thank you for your time. I appreciate it, and I'm sure we'll be talking to you again.
Thank you. You're most welcome.